Hello students, in this session we will discuss some numericals from ionic equilibrium, which is also termed as acids and bases. Right, now this is the first question for us. Which can be an acid and also a base according to Bronsted-Lowry theory? Which can be an acid and also a base according to Bronsted-Lowry theory. What is that? First option is Cl minus, second option is bisulfate, third option is NH4 plus, and fourth option is O power minus 2. Right? These are the four options given for us. Now among them, Bronsted-Lowry theory states that an acid is a proton donor and a base is a proton acceptor. Cl minus can act as only proton acceptor. HSO4 minus can act as both proton acceptor as well as proton donor. And NH4 plus can act as only proton donor. It cannot further accept a proton. It can act as only donor. This is acceptor, means a base. This is a donor and acceptor. So both acid and a base. This is only proton donor. This is only proton acceptor. So as per this concept, among the four options, which can act as both donor as well as acceptor, both acid as well as a base, is bisulfate. Let us see the next question. So next question is about conjugate acid-base theory. So according to this theory, an acid-base pair which differ by a proton is said to be conjugate acid-base pair. An acid and its base, conjugate base, which differ by a proton are said to be conjugate acid-base pair. Now among these options, H2O when donates a proton, H2O when donates a proton become OH minus, right? So there is a proton difference. So this is conjugate acid base pair. H3O plus, it can donate one H plus. After donating H plus, it becomes H2O. So its conjugate base is H2O, not O power minus 2. So this is not a conjugate acid base pair as per the present observation. CH4, if it donates a H plus, it becomes CH3 minus. Its correct conjugate base. So this is also conjugate acid base pair. H2O after accepting a proton become H3O plus. So this is also conjugate acid base pair. So as per the conjugate acid base theory concept, among these four options, which doesn't come under the conjugate acid base pair? Second option. So on every sub-concept, we are discussing one or few questions. So this is about conjugate acid-base theory. Now let us discuss next question. This is another question from Bronsted-Lowry theory of acids and bases. Right? Which of the following is the strongest acceptor of a proton? Which of the following is the strongest acceptor of a proton? Means Bronsted base. Strong conjugate base, they are asking. Strong conjugate base is asked. So the parent should be weak acid, because for a weak acid, its conjugate will be strong base. For a weak base, its conjugate will be strong conjugate acid. So based on this logic, as we are asked to find out strong conjugate base, we are asked to find out strong conjugate base. Its parent should be weak acid. So let's come to their parents. This is HCl. Its parent compound is HCl. This parent compound is H2SO4, right? And this parent compound is HCl, hydrogen cyanide, and this parent compound is HNO3. Definitely, among these four different acids, we can say HCl as a weak acid. As this is a weak acid, its conjugate Cl minus acts as strong conjugate base. So this is another question from Bronsted-Lowry theory of acids and bases. This is our next question from Lewis' theory of acids and bases. See, in this reaction, Cu2 plus is getting surrounded by ammonia molecules. Here these ammonia molecules are as ligands. Ligands means electron pair donors, and a complex salt, complex anion is being generated. Have you noticed this? Now, in this structure, Cu plus 2 is surrounded by 4 ammonia molecules, where each ammonia is donating 1 electron pair to Cu2 plus cation, central metal cation, thus forming this anion. So, according to Lewis' theory of acids and bases, an acid is a substance that accepts electron pair. Lewis base is a substance that donates an electron pair to form a dative bond. Of course, that is a condition. To form a dative bond, they should form a dative bond. See, according to Lewis' theory of acids and bases, what's meant by an acid? Which accepts electron pair to form a dative bond, and Lewis base is nothing but which donates electron pair to form a dative bond. And according to the same Lewis theory, what's meant by a neutralization reaction? Neutralization reaction is the one in which both transfer of lone pair from a Lewis base to Lewis acid, means the step that involves the dative bond formation is said to be neutralization. So, in this molecule formation, anion formation, see, a dative bond is being generated between Lewis base and a Lewis acid. So, this relation or this reaction can be named as neutralization according to which theory? Lewis theory. So, earlier we did Bronsted-Dowry theory questions. Now we did Lewis theory questions. Let us see next question. This is our next question. At a particular temperature, the ionic product of water, ionic product of pure water is 4 into 10 power minus 14 mole square per liter square. 4 into 10 power minus 14 mole square per liter square. What is hydroxyl ion concentration in that water? What is hydroxyl ion concentration in that water sample? See, it is water. At any particular temperature in water, at any given temperature, concentration of H plus will be same as that of OH minus. So, ionic product of water Kw is concentration of H plus into OH minus. This can be given as Kw equals to concentration of OH minus into OH minus, as both are similar. So, OH minus square is equals to Kw. Then, concentration of OH minus is equals to root of Kw, which is given as, Kw value is given as 4 into 10 power minus 14. 4 into 10 power minus 14. So, concentration of OH minus equals to 2 into 10 power minus 7. So, we have to remember that in H2O, at any given concentration, H plus concentration is same as at any given temperature. At any given temperature, H plus concentration is same as OH minus. So, from that logic, we have to solve this. Let us see the next question. So, this is a question on pH scale. pH scale, according to which you know that pH is a negative logarithm of H plus ion concentration to the base 10. Negative logarithm of H plus ion concentration to the base 10. And you also should remember one point. pH can be expressed as a negative logarithm of normality to the base 10. Normality of H plus ion concentration. H plus ion concentration means there we have to finally take normality only. If even though it is given in molarity for a dibasic or tribasic or polybasic acids, finally we have to take it in the form of normality only. Okay, after multiplying with the coefficient, we will get normality value only. Suppose let me explain you. 0.1 molar H2SO4. What is H plus ion concentration? 2H plus SO4 power minus 2. As this is 0.1, 2 into 0.1, it is 0.2 molar. You are taking 0.2 as concentration, which is nothing but its normality, right? If molarity is, how do you convert 0.1 molar into normality? Normality equal to molarity into basicity. 0.1 into 2. 0.2 now. So finally, H plus ion concentration, whatever you are measuring, that we are getting in the form of normality only. That's why, do remember the point. pH is negative logarithm of H plus ion concentration means it is negative logarithm of normality of H plus ion concentration. If you remember this point, you won't get wrong answers with silly mistakes. Now let us solve this question. HCl giving rise to H plus and Cl minus. As this is 10 power minus 3 molar, H plus is 10 power minus 3, Cl minus is also 10 power minus 3. Now we got H plus ion concentration as 10 power minus 3. pH equals to negative logarithm of 10 power minus 3. It's a basic numerical. The purpose of giving this such a simple numerical is to explain you something. Don't feel like we are all aware of this numerical. See here, HCl solution, pH of 10 power minus 3 molar HCl solution. That is the question, no? In this HCl solution, we had taken only H plus ion concentration coming from HCl. Along with HCl, we are also given with the water, which also contains H plus ion concentration. Suppose at 25 degrees Celsius, for example, at 25 degrees Celsius. At 25 degrees Celsius, what is the ionic product of water? 10 power minus 14. H plus is 10 power minus 7. OH minus is also 10 power minus 7. When H plus 10 power minus 7 is also there in the solution, but here we are taking only H plus concentration coming from HCl. We are neglecting the H plus ion concentration coming from water. Why? When compared with this, that is negligible. When compared with this, water degree of dissociation is less, no. So this concentration, H plus concentration coming from water is negligible. Of that reason, we are neglecting that H plus ion concentration. Actually, this is from HCl plus 10 power minus 7 coming from water. This we are neglecting. Till where we can neglect this? When the H plus concentration coming from acid is comparable. Means till this value dominates, that can be neglected. Understood? But when this value is almost near to this value, when H plus concentration coming from acid is almost near to that of water, in such a case we should not neglect. Understood? Means the point to be noted here is, if H plus concentration coming from acid is 10 power minus 6 or less means 10 power minus 6.1, 10 power minus 6.2, 10 power minus 7, 10 power minus 8 max. If H plus concentration coming from acid is 10 power minus 6 or less than that, in such a case, net H plus concentration must be taken as H plus concentration coming from acid and H plus concentration coming from water. In this way, we have to take the net H plus ion concentration. Let us solve one simple question based on this. See, for example, we are given with a question. Calculate pH of 10 power minus 8 molar HCl. 10 power minus 8 molar HCl. So here H plus ion concentration is less than 10 power minus 6, right? What I said earlier, if H plus ion concentration is 10 power minus 6 or less, in such a case, along with the H plus ions coming from acid, we also have to consider H plus ions coming from water. H plus ions coming from water. So now H plus ion concentration, net concentration is H plus ion concentration coming from acid plus H plus ion concentration coming from water. What is H plus ion concentration coming from acid? 10 power minus 8, and that coming from water is 10 power minus 7. So it is 10 power minus 7 into 0.1 plus 1. It is 1.1 into 10 power minus 7 H plus concentration. Now we need to find pH of this solution. It is minus log H plus. That is minus log, what is H plus air concentration? 1.1 into 10 power minus 7. That is minus log 1.1 minus log 10 power minus 7. It is 7 minus log 1.1, 6.96, because this is 0.04. 6.96. So for this question they may give the value 8. First option, temptingly they will give that direct value. Students will be in a hurry to solve it as early as possible in the examination hall. So immediately by looking at this, the previous question 10 power minus 3 molar HCl we did, where fatafat students can answer 3 pH. The same way, by looking at this, immediately they will answer 8 in a hurry. It doesn't mean that students are not aware of the concept. In a hurry to answer quickly, they will immediately go think, it is 8, no? Initially. Even the first option also, to tempt you, they will use 8. But do remember this logic. If H plus concentration is less than 10 power minus 6, then H plus concentration from water also to be considered like this. H plus ion concentration coming from water also to be considered. Now this is the answer. This is the option. This will be given somewhere. Answer will be 7 and this is some 6 and this is because 8 plus 6 14 students may think like that. 6.96. Immediately whatever is given, most of the cases that will be in such models wrong answer only. So we should be very they may give 6.96 in the beginning also, that's not a fixed thing. So we should be very careful while answering such questions. So let us see one more question. See, this is another question from pH of mixture of solutions. See, 100 ml of 0.1 molar HCl is mixed with 100 ml of 0.1 molar H2SO4 with 300 ml of 0.1 molar NaOH. Immediately, a student in general will go to this formula M1V1 plus M2V2 plus M3V3 by V1 plus V2 plus V3. Okay, see, this formula is valid only when they are all mono-basic acids or mono-acidic bases like that. But here it is a mixture of acids and bases. So we should not use a direct combination. Even this formula is also properly valid when you do that in terms of normality. Now what we have to do, first we have to find the normality of mixture of acids and then treat it with the base. So this is not a valid concept. First we have to convert molarity into normality. This is 0.2 normal. This is 2 into 0.1, 0.2 normal. Right? First you find the normality of mixture of these two. Resulting normality of mixture of acid is equals to N1V1. N1 means 0.1 into 100 plus 0.2 into 100 by 200. That is 10 plus 20, 30 by 200. Right? This is the normality of acid mixture. What is normality of base? 0.1 normal. Now this normal acid mixture is being mixed with the 300 ml of 0.1 normal NaOH. 300 ml of 0.1 normal NaOH. This volume is what? 100 plus 100, it is 200 ml. Now, when acid base mixture is given, like this. See, let us simplify this. It is 1.5 written, 0.15 normal. Correct? See, calculation part we should be very careful. So 0.15 normal, 200 ml its volume, 100 plus 100 mixed with 200 ml. Now, when an acid and base are mixed, we have to find their equivalents or milli-equivalents immediately. Like 200 into 0.15, 200 into 0.15, 30. 300 into 0.1, 30. So 30 milli-equivalents and 30 milli-equivalents. When same milli-equivalents were mixed, resulting solution will be a neutral solution. In case if milli-equivalents or equivalents of acid is dominating, then normality of the resulting solution can be calculated as NaVa minus NbVb by Va plus Vb. In case if equivalence of base is dominating, then NbVb minus NaVa by Va plus Vb. So So in this way, according to the situation, we have to see three cases. If equivalents are same, it becomes neutral. If acid equivalents dominates, resulting solution is acidic. Base equivalents are dominating, resulting solution is basic. So this is one question in which 2-3 formulas we have used. In case of finding normality of mixture of same substances, N1 V1 plus N2 V2 by V1 plus V2. Always better you solve these questions in terms of normality only. You will get accurate value. Don't feel if the options are given in molarity, you can convert it back to molarity. Let us see the next question. Now, let's discuss something about buffer solutions. Buffer solution means a solution which resists change in its pH value, even on addition of a strong acid or a strong base, even on addition of a strong acid or even a strong base. By adding a strong acid or a strong base also, if it is resisting change in its pH value, means if it is retaining its pH value without any change, then that is to be buffer solution. Basically, it is of two types. Other types are also there. As per the syllabus limitations, we have to discuss about acidic buffer and basic buffer. Acidic buffer means it is a combination of weak acid and it's a salt formed with a strong base. Acidic buffer is a combination of weak acid, suppose weak acid CH3COOH. When it reacts with a strong base like NaOH, what is the salt formed? H plus will be replaced by NaC. It's a salt formed with a strong base, weak acid, and it's a salt of the weak acid formed with a strong base. Weak acid and it's a salt formed with strong base NaOH. Weak acid and it's a salt formed with strong base NaOH, like that. When it comes to basic buffer, it is combination of weak base and it's a salt formed with a strong acid. Weak base, when it reacts with a strong acid like HCl, NH4Cl is formed. Weak base with strong acid, sulfuric acid, it is formed this one. Now, we will need some questions, numericals on pH calculation of acidic and basic buffers. pH of acidic buffer can be calculated as pKa minus logarithm of acid concentration to salt concentration ratio. pH of basic buffer can be calculated as 14 minus pKb minus log of concentration of base to concentration of salt. This is just to recap. Now let us discuss the numericals. Numericals are models of numericals possible on these buffers. Before going directly to the numerical, first of all we have to discuss what sort of numericals are possible from this. So let us see that. So this is a question from buffers. See, the first model question from a buffer is whether a given combination is a buffer or not. The first possible question is whether a given combination is a buffer or not. For example, predict the buffer. 100 ml of this one combinations are given, acetic acid and NaOH combinations are given, right? Now what we have to see immediately, see everything looks like weak acid and strong base, see. But in that we have to see whether weak acid is left along with the salt formed with that, or salt is left along with the consumption of complete weak acid. These points we have to notice. Like find milli equivalents. I told you already to convert everything into normality. Solve any numerical in normality. Again, as per the requirement, you can come back to molarity. You will get accurate values. Now 100 into 0.1 normal. As basic is 1, it is molarity is equal to normality. 100 into 0.1 normal, how much? 10 milli equivalents. 100 into 0.05 normal, 5 milli equivalents. So this is 10 milli equivalents. This is 5 milli equivalents of base. 5 milli equivalents of base reacts only with 5 milli equivalents of acid and gives 5 milli equivalents of salt. So the resulting solution will be 5 milli equivalents of salt plus unused 5 milli equivalents of weak acid. So in the first option, the mixture is containing 5 milli equivalent of weak acid and 5 milliequivalents of salt formed with the reaction event. So this combination can be called as an acidic buffer. So it may be the answer. Let us see. Next, this one 100 ml of 0.05 molar. It is 5. 100 ml of 0.05 molar 5. 5 milliequivalents and 5 milliequivalents exactly gives 5 milliequivalents of salt. It gives only sodium acetate salt solution. There is nothing else left. So this is not at all a buffer. It is just the product will be a salt solution. Next, 100 ml of 0.05 molar acetic acid. 100 into 0.05, 5 milliequivalents. 100 into 0.1, 10 milliequivalents. These equivalents are more, acid equivalents are less. So acid will be completely used up, giving 5 milliequivalents of salt and 5 milliequivalents of strong base. Strong base cannot form a buffer, you know that, right? So this is also not a buffer. When it comes to this one, 100 into 0.01 normal means 1 milliequivalent, 100 into 0.1, 10 milliequivalents. Even in this also, 9 milliequivalents of NaOH will be left unused. 1 milliequivalent of salt will be formed. It's a strong base and it's a salt with weak acid, definitely not a buffer. So as per this discussion, we can say only the first option is having some milliequivalents of weak acid and rest milliequivalents as it's a salt formed with strong base. This is one question which is based on whether a given combination is a buffer or not. Means the buffer should contain weak acid and it's a salt with strong base, or a weak base and it's a salt with strong acid. With respect to milliequivalents, we can justify this. Let us see another model question from buffers. See, this is a simple question from buffers in the calculation. One of the models of a calculation of pH of buffers. See, the question is concentration of weak acid and its salt, means the model concentration of weak acid will be given and its salt will be given in a buffer, right? Or concentration of weak acid and its salt before mixing a buffer also may be given. In a buffer is given directly, we can substitute. But this is a question where concentration of acid and salt were given before mixing. And after mixing, we have to find and substitute in the formula. This is second model. First model is concentration of weak acid will be given and salt will be given. They prepare a buffer, ready-made buffer, and give its values. So there is nothing to deal with. Just substitute the given concentrations in that formula. That is first model. Second model is before mixing, acid concentration and salt concentration will be given. After mixing, we have to find substitute in the formula. This is second model. Now let us see. Calculate the pH of buffer formed by mixing 100 ml of 0.03 molar acetic acid with 300 ml of 0.01 molar sodium acetate. Right. Now acid and salt before mixing, these are the values. In 100 ml acid concentration is 0.03 molar. When we mix both 100 and 300, now resulting volume is 400 ml. In 100 ml acid is 0.03. In 400 ml what is molarity? M1V1 equals to M2V2. So M2 equals to M1V1 by V2. 100 into M1V1 by V2 is 400. We are diluting, right? So now similarly, in 300 ml molarity of salt is this one. In 300 ml molarity of salt is 0.01. Then in total 400 ml what is the molarity? Again M1V1 equals to M2V2. M2 I am calculating as M1V1 by V2. Now these concentrations belongs to acid in buffer, salt in buffer. These are before mixing. These are after forming as a buffer. These two concentrations we have to substitute in the formula. pH of buffer, acidic buffer equals to pKa minus logarithm of acid concentration to salt concentration. It is 4.7 minus log acid concentration is the one we calculated and answer will be 4.7. This is another basic numerical. Now here a question on salt hydrolysis. You are aware of the concept. Salt hydrolysis means the reaction of either cation or anion or both of a salt with water to give either basic, right, or acidic or neutral solution. When cation gets hydrolyzed, cation takes OH minus and gives H plus, that is acidic. The reaction of either cation or anion or both of a salt with water to give either acidic or basic or neutral solution is called as salt hydrolysis. Right. Now we are having three types of salts that can be hydrolyzed. Salt of a strong acid, strong base cannot be hydrolyzed. Do remember that point. Salt of weak acid, strong base. Suppose CH3COOH when combined with NaOH strong base giving CH3COONa. This is a salt of weak acid, strong base. When this type of salt is subjected to hydrolysis, anionic hydrolysis takes place. The CH3CO minus, which had come from weak acid, as it had come from weak acid, anion is strong base. It gets hydrolyzed first. Anionic hydrolysis takes place, and anionic hydrolysis means suppose A minus is the anion, gets hydrolyzed giving Ha plus OH minus, and OH minus ions are freely available. The other thing is a weak acid HA. OH minus ions are freely available. The resulting solution can be called as basic solution. pH will be obviously greater than 7, and the formula to calculate pH of such a solution is pH equal to 7 plus half pKa plus half lux. Okay, 7 plus something. Have you noticed? pH formula is 7 plus something, and sometimes they may ask you a question on hydrolysis constant, which can be calculated for a salt of weak acid strong base as Kw by Ka. Right? Similarly, for a salt of strong acid weak base, strong acid weak base means suppose NH4OH weak base combined with HCl giving NH4Cl. So this is from weak base. As it is a weak base, its conjugate is strong. A cation is strong. That's why cationic hydrolysis takes place. And cation when H plus, suppose cation is some M plus. M plus reacts with water, gets hydrolyzed, giving MOH, leaving freely moving H plus ions. Freely moving H plus ions. As H plus ions are moving freely, this is a weak base formula. Resulting solution is acidic. pH will be obviously less than 7, and pH formula is 7 minus half pKb minus half lux. In order to avoid confusion, it should be pH more than 7, 7 plus something. pH less than 7, 7 minus something. Have you noticed? And hydrolysis constant KH can be given as Kw by Kb. Whichever is weak component, its dissociation constant is in the denominator. In the first case, acid is weak, its dissociation constant is in the denominator. Now, the next case is salt of weak acid and weak base. In such a case, both cationic as well as anionic hydrolysis takes place. So, it may be acidic solution or basic solution or a neutral solution sometimes. Or sometimes it may be a neutral solution also depending on pKa, pKb values. So, it may be less than 7 when it is acidic, more than 7 when it is basic, neutral solution when it is 7. pH can be calculated as 7 plus half pKa minus half pKb. Right, depending on these Ka, Kb values, pH value varies. And hydrolysis constant, as both the components are weak, in this case weak acid and weak base, hydrolysis constant can be given as Kw by Ka into Kb. Now, let us solve this particular numerical from this salt hydrolysis. See, we are given with a hydrolysis constant of 0.1 molar sodium citrate. Sodium citrate is a salt of weak acid, strong base. Then, hydrolysis constant is asked for calculation. So, what's the formula for hydrolysis constant? We have Kh equals to Kw by Ka. So, Kw is 10 power minus 14 at 25 degrees Celsius. So, usually they specify at 25 degrees. At 25 degrees Celsius, Kw value is 10 power minus 14 mole square per liter square. And Ka value is, what is Ka value given? 2 into 10 power minus 5. So it is 0.5 into 10 power minus 9, that is 5 into 10 power minus 10. So this is how we can calculate hydrolysis constant of given salt. Using the table given in the previous slide, we can calculate. So this is another question from the next concept, solubility product. What is molar solubility of FeOH thrice ferric hydroxide if its solubility product is 10 power minus 38? These are the options given. Actually, solubility product of FeOH thrice is solubility of Fe plus 3 into solubility of OH minus whole cube. See, FeOH thrice solubility is S. Then its Fe plus 3 solubility is S and OH minus is 3S. Then Ksp is S into 3S whole power 3, 27S power 4. Now solubility product is given. Ksp value is 10 power minus 38 equals to 27S power 4. S power 4 I solved. So S power 4 we got it as 3.7 into 10 power minus 40. Now solubility is fourth root of 3.703 into 10 power minus 40. By using the regular method of finding fourth root, 1.386 into 10 power minus 10. So this is one question from solubility product. And another video only based on solubility product questions will be uploaded next week. Okay, based on that you can go through that for your further studies, right?